My quick announcement is that I'm expecting possibly an important phone call. It's one of those ones where they're going to call between a certain time, right? A certain time interval. And if I get this call during class, I'm going to take the call. I'm going to step outside and take it. And then probably, depending on where we are in the class, I'll have about 15 minutes left once I get that call, and then I'm going to have to leave for about 30 minutes. Okay? So if this happens like in the next 15 minutes, we're gonna have the full class, and what I have is a sample of a past semester's midterm that I'm going to hand out, and I'm going to let you all sit and work in groups. And then I'll come back, and you'll still be here, and then we'll talk about it. Okay? Yes? But I'm not going to cancel class. All right, we good? Just real quick about the bonus, because I was talking about it. Some of you turned in. I have not even looked at the bonus. If you emailed me, I haven't even opened those yet. But the most interesting thing was what was happening when x was 0. And when x is 0, you're on the y-axis. And this is a picture of that function. That's a picture of it. And if you look along the y-axis, you can see that along this, there appears to be like this ridge. Do y'all see that? And so when you try and compute capital D when x is 0, I think you get 0. And that's inconclusive. So I just wanted to see if anyone would investigate it a little further. Because, I mean, if those are like little ridges, right? Like if you take a piece of paper and fold it over, I mean, every point along there would be a maximum, wouldn't it? Local, maybe? So anyway, but you have to really kind of get deep into some other things like hold y equal to a constant, and then just investigate the behavior on both sides. And people either did it or didn't. I'm not going to take off if you didn't. I just want to see how people would handle it.
But what if you look at the x-axis?
When y is 0?
Yeah.
That was a little different along the y-axis. Let me see, along the y-axis, I'm sorry, when x is 0 or when y is 0?
When y is 0.
When y is 0, you're right in here, and you don't have a maximum, but I don't think D was 0 when y was 0.
Okay. Yeah, I don't remember. I gotta look.
All right, let's get into today's material. So if you remember from the beginning of last class, we talked about we're trying to find the maximum and minimum values of these functions. And in the first part of this lecture for this section, we did not have any restriction on the domain. And I said that was just like in Cal 1 when we're looking at some function and we're just trying to find local maximums and local minimums. Now what we're going to do is we're going to move into something that is more in line with this situation from Cal 1, which is where we cut or restricted the domain of the function. And when we restrict the domain, right, on a closed interval here, then it will have what we called an absolute maximum and an absolute minimum. There will be a highest and lowest point on the graph if this is a continuous function on a closed interval, right? Okay, so that's where we're going here. But the first natural question is, if you're in Cal 1 and you want to start and stop here, we call it A and B. AB is a closed interval, which means it's all the numbers in between, right? You can plug those into the function, and you can plug the endpoints in, right? We call this a closed interval. If our domain for our functions live in R2, right, then what is a closed interval in R2? Well, we don't call it a closed interval. We call it a closed set. So we have to start, before we get into this, understanding what we mean by closed and bounded sets. So there's some pictures here. A circle is an example of a closed set. This is a closed set. These are not closed. So do you see the little dashes around the edges? That would mean you don't include the boundaries. So like on this one, you don't include any of the boundary. Here you include all of the boundary except one point. That's not closed. Here you include one boundary, but you don't include these. This is not closed. You have to have all boundary points included for it to be a closed set. To be a bounded set is a little more complicated, but the idea is that your set must be finite. So imagine that I have a set here. Okay? This lives in two-dimensional space. We could orient the x and y axes somewhere, x and y. That's a closed set, right? If I include all these and I tell you the boundaries included, that's a closed set. To figure out if it's bounded, we just need to be able to draw a circle around it. If we can draw a circle around it and include everything, then it's bounded. If it's impossible to draw a circle around it, then it's going to be unbounded. So one example of a set that's unbounded would be, let's say, the y-axis and everything out this way. Okay, that's an unbounded set. So our theorems that we have here for this part of this section require that we're looking at a function on a closed bounded set. Then everything that we talk about is okay. If you go outside of that and you start talking about, unbounded, or you start talking about where the boundary is not included, then you have some bigger issues. In fact, y'all know who the Unabomber is? Ted Kaczynski? No? It's been that long? Y'all know who the Unabomber is?
Yeah.
You heard of him before?
Nailed,
He was a mathematician, actually. He was pretty bright mathematician. I forget where he went to school. And then he's decided to just become a hermit and then try and kill people by sending them bombs in the mail. And he was successful for many, many years. And finally they found him in some shed somewhere and they arrested him and he's in jail now. But one of the things that he studied when he was in his mathematics was what are called boundary value problems, which are where you're starting to investigate the way functions behave along these boundaries when the boundaries aren't included, or functions can start acting crazy there sometimes. So we study them at a higher level. But here we're going to include the boundaries and we're going to be happy. That's a little random tidbit of information for you. Useless information. Kind of like the number of ridges on a dime. So one could look at this several ways. One could say, wow, that's interesting. The Unabomber was a mathematician. Or you could also look at it as mathematics makes you crazy and makes you want to go hurt people. Different perspectives. All right, so what does this new extreme value theorem for functions of two variables say? It says, I know this is hard to read, but this is in the book, okay? If f is a continuous function, all right, so it has to be nice and smooth. We don't have any crazy things happening. On a closed bounded set, capital D. So we have a closed bounded set. That is its domain, it's restricted to that. Then f attains an absolute maximum value and an absolute minimum value at some points inside of D. That means it has to find a absolute max and an absolute min somewhere on that domain. It might be, let's just do a simple D, okay, capital D, this is the domain. Closed bounded set, right? The graph of f is above this. Right? We turn it over and it's what we've been looking at before. And somewhere in here, there's some point in here that when I plug it in, I get a maximum, the maximum I'm going to get. And somewhere in here, I'm going to get a minimum. I'm guaranteed both. It might be that the point's in here. It might be that the point's on the boundary. All this theorem says is that we're guaranteed the existence of it. All right? To find the absolute maximum, to actually find it, here's what we do. We find the values of f at the critical points of f in D. So what we're going to do first, okay, first step, is to act like this is not a closed bounded set and do exactly what we did last class. That identifies local maximums and minimums, doesn't it? Then what we do is we find the extreme values of f on the boundary. And this is the big difference. What we're going to do is we're going to say, it's kind of like, again, from Cal 1. we can set the first derivative equal to 0 to find these points, right? From Cal 1. But that tells us nothing about these. So what we need to do is evaluate the function at the endpoints, right? That's what this step is saying. We need to somehow evaluate the function, not at the endpoints, because we don't have endpoints, we have boundary, right? We need to evaluate the function on the boundary and figure out where it's the highest and lowest. That's going to be a little bit troublesome to do that. Then what we do is we compare our answers from here and here. The largest that we get is our max. The smallest that we get is our min. And that's the procedure. All right? Does that kind of make sense? You all have like glared looks on your face. Spring break is not next week. It's the week after. Then you can go ahead and check out for a while. All right, so let's see if we can handle this. We have a function given to us, f of x equals 3 plus xy minus x minus 2y. We want to find the absolute max and minimum values of this function on the closed triangle with these vertices. Okay, so first let's just take a look at this function. This is the function if I do not restrict its domain. Right, there it is. But I only want to look at the domain restricted, let's see, at the point 1, 0, that's here. The point 5, 0, that's here. And the point 1, 4, here. So those are the vertices of a triangle. And I'm going to treat that as a closed bounded set. And just imagine just taking these points and plugging them into the function and throwing everything else out the window. All right? And just looking at that. What's the highest and lowest value of the function on that closed set? Can you all kind of visualize that or not? Yeah? There's the triangle. Okay? That's the two-dimensional triangle that I just drew. That's your domain. This right here, let's see if I can do this. Make that a little bigger. This right here is the domain laying on the ground in three-dimensional space. Do y'all see that? Don't ask me why it's cut off. There's something wrong with the code. I need to plot more points. But okay, are y'all okay with the fact that that's that domain laying on the ground? Okay, here's the surface. If I don't restrict the domain, there's the surface. Okay, there it is. Now, if I restrict the domain, can you all see the part we're talking about there? I'm going to pull the surface with an unrestricted domain out. It's a little easier to see. Hopefully, you can see that. And I'm going to pull it out completely. And then the green is the surface restricted to that triangle. Do you all see that? And if I look at it from the top, it should lay right on top of it, right? Do you all notice some parts of the surface go above our domain and some below? Okay, so the points we're interested in, here we go. The points we're interested in are these points.
These are the absolute maximum.
Yeah, that looks like where we're having absolute max and min, right? And we're going to have to go in and figure it out. Okay, y'all okay with this? So let's talk about, take these points out for a second. Let's talk about if we were just to take, on this triangle, if we just took this line right here, just this line, and plug just that line into the function, what would it draw? Would it be a surface? Would it be a vector? What would it be? If just this line gets plugged into the function, what comes out up there? A curve, right? So I should have, let me make sure I get my lines right here. There's that line. Okay, so there it is in the domain. Do you see the line in the domain right here? If you take each one of these points and plug them in, right? This blue line represents the edge of the surface, that curve, right? Do y'all follow that? Okay. So if I look at just this right here, if I say, hey, let's just focus all our attention on just these points, it really just draws a line, doesn't it? And I can find the highest and lowest points on a line, can't I? Sure, I should be able to. Now, I could do the same thing for each of the boundaries. I could go to L2, which is this black line right here. And imagine plugging just those into the function, and you would get this edge. Now, let me just spin it around so you can see it. Uh-oh, I'm losing it. There it is. Okay, so I have to turn it on the back side to see it. But if you take just this edge and plug it in, some of them go up, some of them go down, right? What shape does this look like? Parabola. Can you find the maximum of a parabola? Absolutely. From Cal 1, you should be able to, right? And then if I take this last line along the triangle, this red one, I have to spin it back this way. Look at it this way. Then there's the red line. Plug those in, you get another line, don't you? And we should be able to find the maximum of a line. That's the way we're going to deal with these. We are trying to look where the function has its maximum here. We're going to look along the boundary, which is going to turn into, in this case, 3 separate problems that we have to do. And then we're going to have to look at the interior, all the stuff inside. But to do the inside, we do what we did last class. Because when we look on the inside, what we do is we forget the outside. We forget the boundary, and we just say, look everywhere and find me the local maximums. Got it? Questions? All right. That's just proving that those points lie somewhere. So check this out. It looks like our minimums are occurring at these vertices, aren't they? Looks like it. But the maximum, this maximum here, looks like it occurs somewhere along this boundary, right? And then the other maximum look like the same height. I can't tell just from the picture. We'll have to work it out and do the math. But that one looks like it's happening at a vertice, like right here at the origin. So I wonder, do the maximums and minimums always, absolute maximums and minimums always occur on the boundary? No, okay, they don't. But you have to check the boundary. In this particular problem, it looks like they're all going to be on the boundary. All right, you ready to go after this? All right, good. I'm glad. So where do we begin? All right, so where do we begin? Well, let's look at the critical numbers, the things that make the partials 0. Why are those important to us? The numbers that make the partials 0 is where we would have any local maximums and minimums, right? So I'm going to find, first of all, the critical numbers. Critical points. Let's call them critical points, not numbers. And so I'm going to set the partials equal to 0. Partial with respect to x is what? Y minus 1 equals 0. And then the partial with respect to y is x minus 2 equals 0. And that's nice, isn't it? X and y are pretty easy to solve for here. 2, 1. It's a lot like the bonus problem was, setting those partials equal to 0, right? Now, what did we do last class at this point? Once we found where this partial was 0, where these partials were 0. What did we do last class?
Evaluated D.
We figured out what D was, right? Capital D? Now, here's the thing. We actually don't need to do that in this. Here's why. If you go back to Cal 1, remember what we did in Cal 1. We found where the derivative was 0, didn't we? And then all we did is we found where it was 0. We took the endpoints. We plugged all of those into the original function and compared, right? Same thing here. I know that this point might be important, but it's the only one that might be important on the entire domain. So there's no need for D. Understand that? There's no need. We're just going to keep that point. Later on, we're going to plug it into this function, and we'll compare it to what's happening on the boundaries. If this turns out to give us a higher value than everything else, it'll be our absolute max. If it doesn't, then, well, at least we looked, right? This is allowing us to look inside. Oh, wait, hold on. We have to make sure this point lives in our domain. Forgot to look. Hold on. We didn't look at that. Let's sketch the domain even though I had it. 1, 5, 4. We had our triangle here. Does this critical point live in there? Does it live in here? Yeah, it's 2, 1. So it's in here, right? So I'm going to put a little check mark. It's in the domain. This is in the domain. That means I need to check it. What if that what if that instead was the point like 5, 2? I wouldn't check it, right? I would just chunk it. Question?
No, I have one, but I've
You're good?
Thank you.
Okay. All right, so that's the first step. Now, the second step, which is the new part, which is what today is about, is trying to figure out what's happening around the boundary. Y'all ready for this? Step 2, find max, min on I always have trouble spelling boundary. I don't know why. A-R-Y? Boundary?
Without the
Boundary, like that? I knew that much. I knew it was a Y at the end. Seriously, my brain gave up on the English language a long time ago. I just gave up. Shut down. All right, so you know how when I was showing you this image, what I did is I broke the triangle down to 3 different pieces, and I just looked along each one. I said, hey, along this edge, we're a line. Along this edge, we look like a parabola. Along this edge, we look like a line. It's exactly what we're going to do here. We've got to break this boundary down into pieces. So let's go ahead and label it now. Let's call this first, and we could pick any, there's not like always do this. You know, I'm going to say from here to here is the first thing I'm going to look at. I'm going to call that L1. All right? So let's talk about L1, then we'll get to L2 and L3. On L1, let's discuss what's happening. On L1. So everything I talk about from here on out is just in reference to L1. Tell me about the points that live on L1. Tell me about all these points. What do they all have in common? Y is 0, right? Y is 0. So they all look like this. It's some x coordinate, and then your y coordinate is 0. Agreed? All points along that line look like that. And there is some little slight restriction, though. X can't be anything, right? X has to be between 1 and 5, closed interval. Or I'll say with x being between 1 and 5. Closed interval. Do you see how this is starting to already look like a Cal 1 problem? I have a closed interval with just x. You'll see that? Now, let's go ahead and plug these points into our function and see what we get. So what would we get if we plugged in f of x, and instead of y, what can I say about y? It's 0. What do I get if I plug in f of x 0 into that? So replace all your x's with x's, all your y's with 0. 3 minus x. That's what you would get, right? Now you're really in a Cal 1 problem, because what you can do is you can imagine this is some function of x right there. And you want to find its maximum and minimum value on that closed interval. Understand? So what did we do in Cal 1 when we had a function of a single variable on a closed interval and we wanted to find the max min? We take the derivative of this and set it equal to 0. And then we take the endpoints and we take the answer to that derivative being 0 and compare them, don't we? That's what I'm going to do now. I'm going to take the derivative of this. Now I'm going to indent this a little bit on purpose, because this is like I'm still working within here. I'm just taking a quick derivative of this, and we're getting what for that derivative? -1. And I'm asking myself, when is that 0? Never. Well, that makes sense. Remember we said when we plugged that line in, it gave us a line? It looked like it did. Well, the derivative is the slope of that line, and the slope we're saying is -1. Okay. So we have no critical points, do we? We have no critical numbers from this. So I'll just put here, there's no critical numbers from this particular incident of moving along L1. So therefore, all I have to do is plug in the two endpoints. So can we do that? Plug in the two endpoints? So what would the first endpoint be? Plugging in 1 for x. So I'm really looking at what's f of 1, 0, which is right in here. 2. Okay, what's the other one? F of 5, 0, which would be -2. Got it? Okay. Save those. We'll come back to those in a minute. All right? All we've done is we've moved along L1. We found that we do actually have a highest value along L1. It's at 2, right? The highest value is 2. The lowest value is -1. Let's just go back and take a quick look at the picture and see if our picture corresponds to this. Try and squeeze it in right there. We were on the blue. Oh, come here. Whoa. Okay. Turn. Can you all tell this is L1 right here? And when we plugged in 1, 0, which would have been this point, it spit out 2. And when we plugged in 5, 0, it spit out -2. All right? And nothing in the middle because this right here, the derivative was -1, right? All make sense? Okay, let's continue to move around the closed bounded region. So let's go L2. Let's let L2 be, well, you want to go with the hypotenuse of this now, or do you want to go the easier one, which is this? You want to do the easier one first? Okay, let's do this one. L2. This green really does not come out good on camera, but I think you can see it enough. All right, so L2. So we set up a whole new piece of information here. So tell me about the points that live on L2. Tell me about those guys. X is always 1, right? In the y coordinate, it varies, doesn't it? It varies from 0 to 4. So all points on L2 look like this. 1 for the x coordinate and y for the y coordinate, where y is always between 0 and 4. So now you're going to plug all those points into the original function. Replace x with 1, y with y. So what's f of 1y? Up there. Yeah. It's 3 plus 1 times y minus 1 minus 2y. So what is it? 2 minus y. There we go. It's 2 minus y. So any questions? If we follow the same procedure now, what we would need to do is find the critical numbers of this, acting as if this now is a brand new function of a single variable. Now, the fact that it's y, not x, let's not let that freak us out. It's the same thing that we had when we had, x in here. We're going to take the derivative of this with respect to y, and this is going to be our closed interval. So what is the derivative of this with respect to y? -1, and that's not ever 0, right? So I don't have any critical numbers there? So all I need to do now is evaluate this function at the two endpoints, 0 and 4. So I need to go f1 of what? F1, 0, and then F1, 4. Understand? And I've had students in the past ask me, do you plug the 1, 0 up into this, or do you plug the 1, 0 into this? What's the answer? This is easier. You're going to get the same result, okay, either way, but this one is less work. We already know what happens when you plug in 1 for x. That's what happens when you plug in 1 for x. We just want to know what happens when you change the y, which is this. So what happens when I plug in 0? 2. And then when I plug in 4, negative 2. Save these. We'll come back to those later. Do you see that we actually repeated ourselves here? We already had found 1, 0, hadn't we? We had done that in the last problem. That's because our two lines, they overlap each other, don't they? They overlap each other? Okay. All right, now we've saved the hardest one for last. Let's move along L3. Do y'all have any questions? So far, it's straightforward. No voodoo magic here. We've been pretty lucky with L1 and L2 because on L1 the y coordinate was fixed. Yes? Oh yeah. On L1 the y coordinate was fixed. On L2 the x coordinate was fixed. Got it. All right. How about on L3? Are either one of the coordinates fixed? As you move along, your x and y coordinates change, don't they? But if they live on the line, there is a relationship. And that's what we need to determine, is what's the relationship between x and y here. So how do you think we're going to find the relationship? Find the equation of the line, right? That's a line. Find the equation of a line. Well, what do I know so far? I have one point here, which is 1, 4, and I have another point over here, which is 5, 0, and someone in college algebra told me once that to find the slope between two lines, it's like y2 minus y1 over x2 minus x1, right? Something like that. So what's the slope of this line, L3? I'll do the work right here. What's the slope of that line? Negative 1? Is it? It is. It's negative 1. But we need the equation of the line, so how would you get the equation? You could use this formula, remember this one? Or there's another one, y equals mx plus b. But if you do that one, you have to know the y-intercept, which you don't, well, you kind of do, but you could cheat by just knowing you go over 1, up 1, but that's fine. I'm just trying to give you a general idea. If this line wasn't so pretty, because it is pretty, it's slope negative 1, but if we didn't have that, then how would we do it? I would probably scrap this. I'd go to this right here. So just pick one of those points as your x1, y1. You have y minus, let's pick this one. This is an easier piece to work with, right? So that's going to be y minus what? 0 equals m, which we said our slope was negative 1. X minus 5. And just clean that up, and we have y is equal to negative x plus 5. Got it? So if we live on L3, right, if you are a point on L3, here's what I can tell you about that point. It has some x coordinate, right? And the y coordinate is always negative x plus 5. That's the relationship between those 2 points. Whatever this is the y has to be that. Yeah? Questions?
Where did you get the x?
This? Just I'm picking an arbitrary x. If I come out here and I say, hey, okay, pick an x, that takes me to here. Now what's the y coordinate going to be? To live on the line, the y coordinate has to follow the equation of the line. So the x was arbitrary. Okay, so now what we'll do is just like we did before, all the points on this line L3 look like this, x, negative x plus 5. And we do have a restriction on x, right? What's the restriction on the x that I plug in to be on this line? Smallest x I can be is 1, the biggest I can be is 5. So I still have this restriction. Plug this into that. You get what's f of x comma negative x plus 5. This is 3 plus x times the y, but the y is negative x plus 5. And then minus x, and then minus 2 times negative x plus 5. You see, that's just the original function with all the y's replaced with negative x plus 5. Anybody have any idea what type of function this is going to be when you put it all together? It's going to be a parabola, right? Because I showed you the picture. When you plug that line in, we got this black parabola, didn't we? This better turn out to be a parabola. It's going to. It's, let's see, 3 minus x squared plus 5x minus x plus 2x minus 10. Clean it up. Negative x squared. Negative x squared. How many x's do we have there? 6. 6 x's. Constant. Minus 7. Boom. There it is. So this is really cool, I think. I don't know. I think a lot of things in math are cool, so I don't know how that translates to you. But what we know right now is when you plug this line in and you throw that into this function and you look above, like if you're standing there on this line, you looked up, it would be a parabola. And it would be opening down because negative in the front, it's going to open down. And so what we want to know is what's the maximum and minimum values of this on this closed interval. So now the derivative is going to matter, right? We're going to take the derivative of that. So what would the derivative of this x comma negative x plus 5 be? Negative 2x plus 6, right? And then from there you set that to 0. F prime equals 0. Well, that's going to be negative 2x plus 6 equals 0. So x is 3, right? X is 3. So we actually have a critical number this time, don't we? If x is 3, can you tell me what point that is over here? Come back to this. If x is 3, where are you? 3, 2, right? 3, 2. Plugging in 3 for those. So this implies that 3, 2 is a critical point. Understand where the 3, 2 came from? Yeah? So what I do now is that's the only critical point I have. What I need to do now is I need to look at this function at this point and at what? X is 1 and x is 5. See, I haven't done that part yet. So I'm going to write those out. So I'm going to look at what happens when I replace the x with 1. So put 1 right here, we get 1, 4, right? Replace the x with 5, I get 5, 0. And then replace the x with 3, I already know what happens. I get 3, 2, right? So I'm taking the two endpoints, and I'm taking the critical point, and I'm going to plug all those into the original function. And let's see what we get. We already know the first two, don't we? Because we already did those, didn't we? Didn't we do that point already? Didn't we do that point when we did L1, L2? What were those? 1, 4 was negative 2, and then 5, 0 was 2? Oh, it was the other way around? It's 2 here? Yeah, 2 and negative 2. Okay. And then what about F32? We have not done that yet, right? We've never plugged 3 and 2 in there. So let's go ahead and do that. Plug 3, 2 up there. We could actually plug, no, that's the derivative. We could plug it into the parabola, but I'm going to just plug it back in up here. So 3 plus 3 times 2 minus 3 minus 2 times 2. What do we have? They're both negative 2? Okay, well, y'all just say something. I've erased it from the board. I don't remember what it was. You're the one who has it written down. Okay, so negative, negative. Wait a minute. Hold on. 1, 4. Oh, yeah, because 1, 4 was up here at this one. Thank you. Okay, so what do you get when you plug in 3, 2? 6, 9. Those 3's cancel. 5? No. 2. You get 2. You get 2. Okay. We've gone around the boundaries, right? The whole boundary we've taken care of. We looked on the inside. We did find a point on the inside. What was that point on the inside? 2, 1? Yeah? So let's put this all together, all right? Let me put all the points that were important to us together up on the board. We had, from the first part of this problem, so I'm on step 3 of this. I'm going to compare now. I have, from the first part of the problem, I got this point 2, 1. From all the different lines, L1, L2, L3, I wound up having these 3 corners. And this one up here, which was 3, 2, right? Does that cover everything? Is that all the points we got? The one here, the 3 corners, and then that 1, 3, 2, 1 right here. Right? That's all of them? Yeah. And now let's just, we already know all their values, right? Let's just write their values down. Oh, we never got, which one did we never get? 2, 1, right? We never got that one? This one was 2, I believe. This was negative 2. This was negative 2. This was 2. Find the value at 2, 1. Plug in 2 for x and 1 for y. 1? All right. That's everything. Now we just need to draw our conclusion. No questions? What is the maximum value of this function on this closed bounded set? 2. The maximum value is 2. Where does it happen? Here and here, right? At 2 places we have the absolute maximum occur. Where does the absolute minimum occur? 2 different places, right? The value is negative 2. So there's different ways we can actually write down this conclusion, right? We can just simply state it, write down all the points. I'm going to kind of show you both ways. The absolute maximum is 2, all right? The absolute minimum is negative 2. Now, if I want to put where they happen, then I could just list the points as ordered triples. I could say 1, 0, 2, and 3, 2, 2. This is where I get my maxes, right? And then I could say, let me see, 5, 0, negative 2, and 1, 4, negative 2. Those are where I get my minimums, right? You should be comfortable stating it either way. The reason why we want to just be able to say what the max is and the min is because a lot of the problems that we would deal with that are like real world or like word problems, that's all we're looking for. And in other problems, you want to know where it happens. And so you would want to know more information like this. Okay. Wow, that only took about 40 minutes. May I? I think what we'll do on this one is we'll do all the maths first. After we're done with all the, have you ever hear like a lot of Europeans say maths?
Yes.
You heard that? Okay. All right. So we're going to do all the maths first. And then after that, we'll compare it with the picture. All right? So we have an absolute maximum, and we're looking for the absolute maximum minimum value of this function. On the rectangle, D is equal to the set of x and y such that x is between 0 and 3 and y is between 0 and 2. So we have to understand what that means first. This is set notation. It's all ordered pairs in two-dimensional space where your x's are bounded between 0 and 3, your y's are bounded between 0 and 2. What does that look like in two-dimensional space? Rectangle? X values are between 0 and 3. So all I know is that the points, the x values have to live between here and here, right? So your x's could be anywhere in here. But your y's have to be between 0 and 2. So it could be anything in here, right? And so what you need is both of them together, which is where they intersect, which is this right there. So we're looking at this rectangular region. It's closed and bounded, right? As long as these inequalities were included the equals, right? Then it includes the boundaries. All right, there's our region. How would you like to go about this? What should we start with? Find the critical points from what we did last class, right? Set the partials equal to 0. All right, so go ahead. Do it. I'll do it up here. I won't say anything. I'll just kind of. I don't like what I did there. Y'all got the partials yet? Set to 0? Got a solution? So your first partial set equal to 0, all you get is the relationship that x has to be y. That doesn't tell you enough. But the other partial equal to 0 tells you x has to be 1. And if x has to be 1 and y has to be x, then y has to be 1. So that's your critical point. Now we need to double check to make sure. Does it live in here? It does. It lives in there. So check. We will plug that into the function. You want to plug it in now? Just may as well like figure out what the value of the function is now. We don't know if it's a max or min or anything, but let's plug it in. F of 1, 1 will be, is it 1? Yeah. Save that for later. I've had students on tests, the one that you're going to take in class next week, I've had students on tests forget to do this step. They do all the boundary, they move around and all that. They forget to do the partials equal to 0, and I take off a lot of points because this, you have to check that number. I mean, you have to check that point. That could be the highest point, could be the lowest point. If you forget about it, then it's like forgetting to check one of your endpoints back in Cal 1. You're just like checking part of it, not everything. All right, that part's done, yes? Now, we're going to move around this closed bounded set. So we're going to break it up into how many different pieces here? 4, okay? 4 pieces. So here's what we'll do. Let's define this to be L1, and let's go clockwise. L2, L3, and L4. What I'd like for you to do is let's let these tables right here, these 2 tables, we'll do L1, okay? These 2 tables will do L2. These 2 tables will do L3, and I will do L4, okay? So y'all work out L1, y'all work out L2, y'all work out L3, I do L4. And we'll talk in a second. You do your work, I'll do mine. And y'all can talk to each other. Got to turn my microphone back on. Oops. Oh well. Shit happens. Can't do anything about it now. I even, when I walked out, I almost reminded you, I was going to remind you to tell me to turn it back on. Okay, it's on now. First quadrant, and then I have to be inside a circle of radius square root of 3. So here's root 3. Here's root 3. Everything in there, including the boundaries. Right? So we start by first looking at the partial, setting them equal to 0. So what's the partial of f with respect to x set equal to 0? That's y squared is 0. Next, partial with respect to y equal to 0, which is 2xy must be 0. Well, this already tells me that what? Y has to be 0 in order for that to be true. And over here, shit, what does this mean? How do I make this one true? This says y has to be 0, right? So over here, does x have to be 0 for this to be true? No? Why not? Because if y is 0, then it doesn't matter what x is, does it? If y has to be 0 to make that true, then y has to be 0 here, and then you can let x be whatever you want it to be, right? So we actually have x is free. Call it free variable. It's free to be whatever it wants to be. So we have an infinite number of points that satisfy this, don't we? They all look like this. They all look like that. Do you agree? Any point that looks like this will satisfy these two equations. Thank goodness, though, these points coincide with what? This is your x-axis, isn't it? That's what this is. This is your x-axis. And it turns out that that's the boundary of one of my sides. So we got lucky that the only critical numbers or critical points we're going to get from this right here is actually what we're going to be looking at in just a second. So what if we didn't? What if we didn't have that? What if that was somewhere inside here? Well, then we would have to plug these into that and figure out what happens. It would be almost the same exact story. We plug those in, figure out what that is, and then take the derivative. Okay, so let's move along these. L1, I'll call this L1, will be along this edge. L2 here. I shouldn't call that L3, right? It's not straight. So I'll call it C1 for curve 1. So I'm going to go around L1, L2, and C1. I think we can move quicker through this one. On L1, tell me what the points look like. X0, what's my restriction on x? 0 to root 3. Okay, plug in x0 into the function. Oh, come on. 0. Which means I can stop. It means that if you plug any point in along this edge, the function spits out 0. Right? That's what that means. I don't need to keep on doing any work, right? Take the derivative of 0. Go ahead. I mean, right? I mean, there's no need to do this. We're done. That was nice. L2. What do all the points on L2 look like? 0y. What's my restriction on y? 0 to root 3. And what's f of 0y look like? 0 again. Same exact story. It could potentially be that 0 is my minimum. It could be potentially that my 0 is my maximum. I'll have to check in a second. Now let's move along C1. So C1's the harder part. So along C1, what do my points look like? Dun, dun, dun.
Is it 1, 4, something?
Okay, so if I come in here and I pick some arbitrary value right there, and I call that x, then how far up am I going to move? So if I call this x, then what's my y coordinate going to be?
We're gonna make a triangle.
X cubed.
Yeah, you could basically take this as an equation, solve it for x.
The point wouldn't, well, for that line, wouldn't it be sine t, cosine t, but restricted?
Yeah, but that's if we, yes, we could do that. But now what you're doing is you're reparametizing the curve. We would like to have everything in terms of x because of the derivative we're going to take in a second. So you're turning it into a vector function, which you could still do. But I think it's too much work for us. We don't need it that much. Square root of 3 minus x squared. So, well, you tell me. What coordinate is this? It's the y coordinate, right? So what you're doing is you're trying to solve for the y. So you solve for y here. You move x squared over. You take the square root. I'm only looking at the positive root. Why? I'm on the top half, right? I'm on the top half. Understand? Yes? Now, what's my restriction on x? 0 root 3. So I have to pick an x that comes from between here and here. All right, now I get the pleasure of plugging that in. So I'm going to plug that into the function. What's f of x root? Ooh, I'm going to get lucky. That is x times y squared. Square that. Oh, nice. That got rid of the root for me, didn't it? Happy. I'm happy. And this is just 3x minus x cubed. Agreed? Now let's find the critical numbers of this. We've never had a cubic, right? We've had a line. We've had a constant. Like along this one, it was constant. We've had a parabola. We've never had a cubic. Well, anything can come out of these. It just depends on your boundary. It depends on your function. You just now need to be able to take derivative of this. So derivative of f of x root 3 minus x squared is 3 minus 3x squared. And now you're going to set that equal to 0, right? So set equal to 0. And you get x is what? 1 and negative 1?
Yeah.
Right? Plus or minus, but why not negative 1? So you get x plus or minus 1, but because x equals negative 1 does not live inside of, where is it, here? We throw it out. So, got it? So that means I need to look at a couple of things here. I need to look at, from here, f of, let's do the endpoints. I plug in 0, right, for x. I get 0, and then when I plug in 0 here, I get root 3. I need to look at f of, now let's plug in root 3. So that gives me root 3 what? 0. And then I need to look at the most interesting one, which is x is 1, which means that the y value is what? So just 1 in here, you get root 2. And figure out the values of the function at each of those. How about the first two? 0, right? If I plug in 0 for x, that's gone. Plug in 0 for y, that's gone. So we already knew that, didn't we? We already knew that along these two edges it's 0. So at the corners, or at the two ends of my arc of my circle there, I'm going to be 0. But at that point, 1 root 2, I plug it in and I get what? 2. So can we conclude now? Are we good? We done? Do you have enough information, you think, now? What's your maximum value? Maximum value is 2. Where does it happen? 1 root 2, 2. Yeah? What's the minimum value? 0. Where does it occur? It's a little more interesting, right? How do you answer that? It answers. Anywhere where you have x 0, you're going to get 0, right? As long as x is between 0 and root 3. And anytime you have 0 for x, and who cares for y, and as long as your y is between 0 and root 3, that's where you're going to get your minimums. So we're saying, that's just how we say along this edge and along this edge. Make sense? Shall we take a look at the picture? All right, let's take a look. Was that a question? No? Okay. There's your domain. There's a domain on the ground. Here's the surface. Weird looking thing. Here's the surface restricted. Okay. And there are the points that we found. Now, I actually did not include, I should include every point on this edge, right? Those are my minimums. Every point on this edge are my minimums. But you can see that part right there. There's our maximum right there. All right? Okay, last one for this section. I think that the page number on that might be wrong. Someone can check on that in a minute. But all right, so let's do a word problem. Find the largest rectangular box with edges parallel to the axes that can be inscribed in an ellipsoid in this ellipsoid. So look at it this way. You have an ellipsoid, right? Here it is. The orangish thing is the ellipsoid. And we want to put a box inside of it. And we want it to be inscribed. When we say inscribed, that means that this point, this point, this point, and this point touch the edge of touch the surface, right? And the bottom edges touch the surface inside. That's what it means to inscribe it. I want to find the largest volume possible. Does this look kind of like a Cal 1 problem? Maybe, maybe not. So look, if I go really tall, what happens? I get a very tall box, right? But it's very narrow. And look, the volume right now is 1.7. I'm having the computer calculate it for me. If I change, make my y value and my x value bigger, you can see I'm getting a bigger volume, right? 6 now. But if I go too far, see if I go too far, what happens is that you're getting more width, but it's shorter. So there's got to be some optimum solution, right? Some optimum. This is an optimization problem. But now we are armed with being able to treat this as a function of 2 variables instead of a function of 1. Okay? Understand geometrically what we're trying to do? Okay, here we go. What are we trying to find the maximum of? Volume, right? We want the maximum volume, which means that you now need to tell me what the equation of the volume would be then. If you're trying to maximize volume, you better be able to express that in terms of some variables. So I'll start you off. V equals. Okay, what is it? X times y times z. Let's go back to the picture for a minute. Now remember, we're in three-dimensional space, right? So I have a little thing here that might help us out. Whoa, I don't know if that helped out at all. Why did the other one go away? Okay, look at this point. Can you all see that black point? That's in the first octant, isn't it? That point has the coordinates. You start at the origin, you go out x, right? You go out y, you go up z. That has the coordinates x, y, z. So if you say the volume is x times y times z, it's going to give you the volume of that box. Is that what we're talking about? Is that the box we're talking about? I want one bigger. So I want this point right here to touch the edge of the ellipsoid, right? So what's missing from this? What else do I need? The other 7 octants, exactly. There's another rectangle you need, or another box you need in the second octant, another box you need in the third octant, in the fourth octant, fifth, sixth, seventh, and eighth, right? So I agree with you. X times y times z will give you the volume of that box. The volume of the whole thing is 8 of those. So the volume should be 8 x, y, z. Agreed? Understand? So that's why I pulled that in there. I took this out. Now, I think if I do that, you can see it. See that? That's just one of the 8 pieces. We agree? Okay, we're trying to find the maximum. I'll leave that. We're trying to find the maximum of this function, aren't we? Its highest value. Right now, this volume function depends on how many things. For us to be able to talk about volume, you must be able to give me x, y, and z, right? Can we find right now the maximum of a function of 3 variables? What have we been doing the last 2 classes? Finding the maximum and minimum of functions of 2, right? So we can't handle this right now, can we? But there's something that we're missing here. This point can't just be any x, y, z. It can't just be anything, right? It must live where? On the ellipsoid, right? This point must also touch the ellipsoid, which means that it must satisfy the equation of the ellipsoid. So let's go back up to the ellipsoid, and let's take a look at that equation, and let's talk about that relationship. I just need, if everyone agrees, I just need to try and convert this into a function of 2 variables, then I'm in business. Yeah? Yeah? Okay. So I would like to get it maybe to a function of just x and y. 2 variables. Can I do it? How? Solve for z. That's it. Look, if that point x, y, z has to live on this, then the x, the y, and z have to satisfy that equation. So solve this equation for z right now. Let's solve it for z. You get 4z squared equals 36 minus 9x squared plus, minus 36y squared. And then divide by 4. Z is 9 minus 9/4 minus 9y squared. I forgot my squared. And then square root. Yeah, I forgot the x squared. That's not going to be a good thing. And so we have square root of 9 minus 9/4 x squared minus 9y squared. Now, it should be plus or minus, right? But we are just going to be looking in the first octant because everything else is just 8 times that. So everyone keep that in mind. What we're doing is we're imagining that we are restricting ourselves to the first octant, aren't we? Restricting ourselves to the first octant? So now just rewrite the volume equation. 8x, y, and yes, this is z. It isn't pretty. Now you can guarantee me that this point lives on the ellipsoid, doesn't it? That point lives on the ellipsoid. It's a function of two variables, and I want to know the maximum and minimum values of it. So now my question to you is, am I going to approach this the way we did last class, where I'm going to let the domain be everything? Or am I going to have to look at the maximum of this on a closed-bounded set? What do you think? Closed-bounded? Yeah, because you can't, there are some restrictions on that x, right? That x can't just take off, all the way, just keep on getting bigger and bigger, because you have to live on the ellipsoid. The ellipsoid has some restrictions, doesn't it? So let's see if you can help me get what the domain is. So we're going to be looking on a closed-bounded set. So the domain must be closed-bounded. In 2D. How do I get it?
So that thing is larger than where you put two. Well, how do you put two?
Solve for, how do you mean solve for y? Okay, so yes, I agree with you, but there's something, let me go back to the picture. Might be a little easier to see. I'll have to erase what I just wrote. What I'm going to do is I'm going to flip this picture over, and we're going to look at it from the top. Okay, let's look at it from the top. Ooh, that's pretty good. Yes? I can change my values of x and y. It's hard to tell. I'm still touching the ellipsoid here, but I am. Right? Do you see that there's, I can let x go from 0 all the way out to some value, right? And y go from here to here, but I can't get to this point, right? I'm not supposed to go there. So my boundary is actually this curve along with this and along with this. Do y'all see that? That's what I need to come up with my boundary L1, L2, and C1. Let's talk about L1. If this is the x-axis, this is the y-axis, how would you get this L1? Well, what do you know about those points? They all look like this, right? What's the restriction on x? 0 to something, right? So I heard someone say this. Isn't this picture we're looking at basically taking the entire ellipsoid and smashing it down to the xy plane? So basically letting z be 0, right? If z is 0, I'm just like taking a slice right through the middle of the ellipsoid. So I'd like for us to go to the equation, back up to this, and I'd like for us to let z be 0. If we let z be 0, then we have the rest of what's there is an ellipsoid. Okay, so let's look at that. 9x squared plus 36y squared equals 36. I'll divide everything through by 36. 9 divided by 36 is 1/4 plus y squared equals 1. Now that is definitely an ellipsoid. What is this value right here? What's the biggest it can be?
Is it the square root of 4?
Yeah, so tell me, if I live anywhere on here, right? If I'm on the x-axis, what's my y-coordinate? 0, right? Take that y out of there and solve that for x, and what would you get? It's 2, right? Plus or minus 2. So this is 1, and then the other one's on the other side, but we're not looking at that one. So this is 2, yeah? Now do the same thing over here. This time, x is 0. Plus or minus 1? So this is 1. Understand this? The last thing we need to get, I think from this we can get L1 and L2. All right? We'll be able to talk about those points. What about C1? What do we have to do to get C1? That's right. We know that for C1, I'm going to have a point on here. It's going to have some x coordinate, right? And then the y coordinate is going to be this solved for y, which is the square root of 1 minus a fourth x squared. Move that over, square root. Do y'all feel okay with this? It's a lot to swallow. The fundamental idea is pretty simple, okay? The idea is that if you have a function of two variables and you have some sort of closed bounded set, then all you do is check the inside, check the boundary, compare, and you're done. But those boundaries and setting them up and figuring out what they are can be a little bit involved. All right, let's do this. And I'm not looking forward to setting the partials equal to 0 either. But I have 10 minutes, so I should be able to do it. All right, we all good with that? I'm going to have to erase, but are we all okay with that? Here we go. All right, starting up, now that we have an idea what the domain looks like, start out, first step, I need to set partial of v with respect to x equal to 0. So what's the partial of v with respect to x? Product rule, yay! So, what, 8y, square root of a bunch of junk, right? Plus, what's the derivative of the square root of a bunch of junk? 1 over 2 square roots of all that junk, right? Times the derivative of what's inside with respect to x. What's the derivative of what's inside with respect to x? Negative 9 halves x. But then, times, finish your product rule off, 8xy. Okay, remember this, right? So derivative of this with respect to x was 8y times the root. That's this. Derivative of the root of something is 1 over 2 times the root of that something, times derivative of what's inside. Derivative of this, 0, 0. That, bring the 2 down, reduces the fraction to negative 9 halves x. And then finish off product rule, 8xy in front. I need to set that equal to 0, folks. All right, so let me clean it up. 8y root junk plus, let's see, this is a 2 down here and a 2 down here, which is a 4. This 4 goes into 8 twice. So I get negative 18, so minus 18 x squared y over root junk equals 0. Can you put these two together? Common denominator, can you? Hope so. Let's see. What happens if I try and put those two together? Well, I have to put this root on the bottom of this one, right? And on the top. And when I put this root on top, the root goes away. So I'm going to have 8y times the junk that was under the root minus 18x squared y all over the common denominator, which was the root of the junk, equals 0. And I think I can go fill the junk in now. All right, let me go fill that junk in. I have to erase. I'm not going to have enough time. 8y, the junk was 9 minus 9/4 x squared. I forgot. Minus 9y squared? That was the junk? Double check, yes. Minus 18 x squared y equals 0. Distribute 8y through. And what do we get there? Is everything all right? We good? Okay. What do we get when we distribute that through? 72y minus 18x squared y minus 72y squared minus 18x squared y, where? Y cubed, yes, thank you. Minus 18x squared y equals 0. Any like terms there? These are like terms, right? 72, yes, algebra, here we are. Hello, haven't seen you in a while. 30, I guess I should write the variable there. Minus 36x squared y equals 0. Divide by what? 36 is a factor of all those. Y'all want to do that first? So 2y minus 2y cubed minus x squared y equals 0. Pull a y out. Then I'm left with a 2 minus 2y squared minus x squared equals 0. My goodness. So y equals 0 is an answer. Right? Y 0 is one possibility. You got to set that equal to 0, right?
Inequality.
How in the world are you going to do that? This is a, what is that? If I set 2 minus 2y squared minus x squared equal to 0, that is an ellipse, isn't it? But let's just save this, because this was only the partial with respect to x. We have another equation to work with, don't we? And we can work with them simultaneously, because we have to solve them both at the same time. So we haven't looked at it yet, but what would the partial with respect to y be? Okay, so we're going to run out of time. Would you like to attempt the rest of this for? I hate offering bonus. I'm so buried right now with work. But I'll offer it as a bonus. Okay? Only just so you can, go and try and mess with this. No, let's talk about what you have to do still. You have to do this equal to 0, and you try and solve these two. And if you get an answer that works for both, then you need to make sure it lives in your domain. Right? Make sure it lives inside that original ellipse, which is where we turned it over and looked at it from the side. Then, after you're done with that, you have to move yourself around the boundaries. When you move yourself around the boundaries, L1, L2, and C1, then you got to figure out maxes and mins on that, and then you compare them all. To me, this looks like it's probably the hardest part of the whole thing, is this part. All right, well, oh, I have some stuff for you. Okay, so I have your next mini exam, which is not due until the 23rd of March. That's, I believe, is that the Wednesday after spring break? That's the Wednesday after spring break. You should be able to do everything on this mini exam. I'm sorry, I take that back. You should only be able to do up through 4. Number 4 right now. There's 8 problems. You should only be able to do up through 4. Numbers 5, 6, 7, and 8 all require some stuff from Lagrange multipliers, which is the next section, which I will start on Monday. Remember, Lagrange will not be on the test. So everything we've done up to this point, right here, that's what's going to be on the exam. Cut off right here. All right, so y'all want this now? Yes? And then I have, by request, I have a copy of an old exam that I gave in a Cal 3 class as a midterm. Now, when you look at this, keep in mind this was a summer class, and so their classes were 2 1-hour, 40-minute classes together into one. So they were there for like 3 hours or so. That's how much time they had for this. your test cannot possibly be this long. But as far as content, this has a good sample of some stuff. I am in no way saying that this is exactly your midterm. I'm just going to go change numbers. But it gives you some idea of the type of thing I gave them. All right? So how about we do this? I'll just put these on a table, and then as you leave, you can just pick them up. Okay? Why don't we put them over here? There you go. Everybody have a good rest of your day.